So page 638, number 9, we're just trying to find the probability that we're between these two given z-scores. And the directions say find the percentage of total area under the standard normal curve between the given z-scores. The area under the curve is actually the same as the probability. That's how the curve works. So what the directions are really asking is find the probability that you would be between those two numbers. So the simple explanation is you just look up both the numbers and just straight from the chart look up what the numbers are associated with each of those z-scores, and then you just subtract the smaller one away from the larger one, and you get the chance of being in between is 0.077. Now to kind of illustrate why we do that, so for 0.283, so quickly here to just draw a rough sketch of the normal curve here. Alright, so right here would be the mean, right in the middle when it's where it's the tallest. Alright, and then so the first z-score is 0.283, so that means we're 2.83 standard deviations above the mean. So that's pretty far up there. So 2.83 standard deviations above the mean. So the probability of being less than that would be being anywhere less than that. It's going to be pretty high. And we can kind of illustrate that by being any number that's colored in there less than 2.83. And the probability of that we looked up was 0.9977, really high. But the problem's actually asking between 2.83 and 1.41. So 1.41 would be 1.41 standard deviations above the mean, which, a rough sketch, it's about right here. So what's actually the chances of being between those numbers? Well, we have this shaded in part that's everything less than 2.83. What we need to do is just subtract off this part we don't want, because all we want is in between. So we subtract off, color it white. Oh no. Let me try one more time here. Alright, so when you subtract off everything less than 1.41, you're left with just what's in between. And that's what we're doing here. We get the probability of everything less than the 2.83, and then subtract off the part that we don't want, the part less than 1.41, and then that leaves you with just the part that's in between. Alright, so that's number 9. So I think I actually did 24 here by accident, but they're both very similar. The average life of the light bulbs for number 24 is 1200 hours with a 50 standard deviation. And again, it's between two numbers what we're trying to find the probability. Now to use the chart full of probabilities, we have to have z-scores. So you're going to want to find the z-score for those two given numbers that we're trying to find the probability of being between them. So to find the z-score, you take the numbers, subtract the mean, divide by the standard deviation. So 1150 is actually one step below the mean, so it's -1 because each step is worth 50. So we're -1. 1150 is -1 below the mean, and 1300 is 2 steps above the mean. If you counted up by 50, you would go to 1250 and then 1300. So 2 steps, or just use the formula 1300 minus 1200 divided by 50 gives you 2. Okay, so we convert to z-scores. And again, we're just going to look up both of those z-scores in the chart and then subtract the smaller one subtracted from the larger one, and so there's actually a 81.85%, or 0.8185 is the probability of being between those two numbers. Or in context of the problem, 81% of our light bulbs, 81.85, last between 1150 and 1300 hours. So 646 here, number 17 is a two-part problem, A and B. And so we're actually dealing with a binomial situation again here, and the problem actually alludes to that. It says that the units of food is binomially distributed. So it's going to be, like, let me scroll really quickly back to the very top, it's going to be a lot like this problem with the prescription drugs. We had a binomial situation. The quick way to figure out the answer, and it's a really good way because it's very close to exactly being right, is to approximate it using that chart full of probabilities. So remember how here we were looking for less than 79, but we actually used 79.5. You always adjust by half a step when you use that approximation. We're going to do the same thing with this problem here about how much animals eat. So the most this given animal can eat is 120 units of food, whatever that means. We can pretend they're talking about people, and it's 120 chicken nuggets. That's the most somebody could eat. And the probability that they'll eat over a given amount of time is 0.6. So skip this line for right now. Let's go ahead and look at the mean and standard deviation here. So the average we would expect that animal to eat would be 72 units of food. So maybe the illustration of people and chicken nuggets doesn't work so well because no one eats 72 chicken nuggets. But whatever animal we're talking about here, the average that we expect them to eat is 72. And this is a binomial situation. Either they eat some food or they don't. There's only two options. And so we got to figure out the mean, 72. And the standard deviation, use that formula. We get this number. Okay, so the first part A, says the probability that they eat exactly 80. Now, to figure out exactly 80, you can use the binomial formula. But for most calculators, probably the calculator you have, it's going to be very hard. Go ahead and try to type in 120, choose 8, and you get some super huge number. And then type in 0.6 to the 80, and that number is extremely small. There's like maybe 17 zeros or something before any of the actual digits start. So to keep track of numbers that small and that huge, your little calculator won't do it well, and your answer is going to be off, and it's really tedious to keep track of such large and such huge numbers. So again, we're going to want to approximate using that chart full of probabilities rather than plugging in straight into the binomial equation here. So remember, when we approximate, we always adjust by half a step. So for exactly 80, we're going to adjust that for the exact number by going a half a step below and a half a step above and finding in between that range, because 80 is right in between those two adjusted numbers there. So again, from here, it's like from chapter 10.4, we just look up the z-scores and then use the chart, because we're going to use that chart now to approximate. So for 79.5, you take that number minus the mean, divide by the standard deviation, you get that z-score. For 80.5, you get that z-score. And just look those numbers up in the chart, and you get them. Subtract the small one away from the larger one, and you get 0.0238. And if you round it a little different, either with the standard deviation, I think the book maybe has 0.0237, but that's just a rounding difference. It's almost exactly the same. Okay, and then part B says at least 70. So again, we have to adjust by 0.5. So we want 70 or more. So this time, the 0.5 adjustment, we need to go down to 69.5. We go down because 69.5 or more includes the 70 or more. Like again, we don't want to adjust the wrong way. If we adjusted by 0.5 up to 70.5 and did 70.5 or more, that would leave off our original number, which we don't want to leave off to 70. That's what we're actually set out to try to figure out. So we adjust down by 0.5 in that case. So if you're doing a more than, you're going to adjust down by half a step. And to jump back from the very first problem, we did a less than 79. That's when we adjusted up for the less than, up to 79.5. But just make sure your adjusted range includes your original number. So in this case, our original number is 70. We need to adjust down. All right, after you make that adjustment, you're just plugging, finding out the z-score and looking it up in the chart. So 69.5, subtract the mean, divide by standard deviation. You get this for the z-score. And then you just look up the chart to find the probability of more than that z-score. Remember, the chart only gives less than. So there's two ways to do a greater than, and one way is just to look up the opposite. So in the chart, I just looked up 0.47. And when you look up 0.47, you get that. Because the chart is perfectly symmetrical, I'll switch back to my paint here, which isn't perfect, but right from the mean, it looks the same on both sides. It slopes down. So when you're doing the opposite, instead of doing less than, when you're doing greater than, you look up the opposite. Okay. The other way you could do it is to actually look up negative 0.47. So let me do that right now. Negative 0.47 is 0.3192. 0.3192. All right. And then, so that's everything less. So this is, to write that out, that's the probability of being less than negative 0.47. So what we want is actually greater than, which would be everything we've left off, so minus the 0.3192. You can do the 1 minus trick if you like that method better and actually look up the number that's been given to you. I'm typing that in wrong. 1 minus 0.3192, and you get 0.6808, which is the same answer. So my preferred method that I personally like is just looking at the opposite if you're finding greater than, which is the opposite of less than. But you can also look up the number that's given, which tells you the less than, and then do the subtraction.